Today we are sitting down, we are locking in, and we are going deep into one of the most extreme, most fascinating, most brutal places that exists anywhere on this entire planet Earth. And I want to start this video with a question. A simple question. When you think of the coldest place on Earth, what comes to mind? Like honestly, pause for a second. What pops into your head? The North Pole? Siberia? The top of Everest? Maybe some frozen tundra in Canada or Alaska? Because here's the thing. Whatever you just thought of, it's wrong. Every single one of those places, as cold as they are, as brutal as they can get, none of them even come close to the actual answer. The coldest place on Earth is Antarctica. And not just by a little bit, by a margin so enormous that it almost doesn't seem real. Let me give you some numbers right now, right at the top of this video, just so you understand the scale of what we're talking about. The coldest temperature ever recorded in Siberia, which most people think of as like the gold standard of cold, is around -67 degrees Celsius. That was in a town called Oymyakon, in Russia. -67. People actually live there. It's a real town with real residents, and it is absolutely brutal. -67 Celsius. Remember that number. The coldest temperature ever recorded on the summit of Everest, the highest point on Earth, is around -60 Celsius. -60 at the top of the world's tallest mountain, where the atmosphere is so thin you can barely breathe. Now, Antarctica. On the 21st of July, 1983, a team of Soviet scientists at a research station called Vostok, sitting deep in the East Antarctic interior, at an altitude of 3,488 meters above sea level, recorded an air temperature of -89, 2 degrees Celsius. -89, 2. That is -128. 6 Fahrenheit for my American viewers. Let me put that in perspective. Siberia's record cold? -67. Antarctica just casually beat that by more than 22 degrees. Everest's record cold? -60. Antarctica beat that by nearly 30 degrees. At -89 Celsius, exposed skin freezes in seconds. Not minutes, seconds. Diesel fuel, which is used to power vehicles and generators at Antarctic stations, turns to gel and stops flowing. Standard steel becomes brittle like glass and can shatter if struck. The moisture in your breath, every single exhale, crystallizes instantly in the air in front of your face before it even has a chance to disperse. Old Antarctic explorers and researchers have a name for that sound. The sound of your own breath freezing. They call it the whisper of stars. That record at Vostok stood for nearly 3 decades as the coldest temperature ever officially recorded on the surface of our planet. And then, it got broken. In 2010, scientists from NASA and the United States Geological Survey were analyzing satellite thermal data from Antarctica, basically reading the temperature of the surface from space. And they found something that stopped them dead. Pockets of temperature in the East Antarctic Plateau, far from any research station, that had plunged to -93. 2 degrees Celsius, -135, 8 Fahrenheit. Now let me put that in perspective for you. The average surface temperature on Mars. Mars, the red planet, our neighboring planet, 78 million kilometers further from the sun than we are. The average surface temperature on Mars is around -60 Celsius. Those pockets on the East Antarctic Plateau were colder than Mars. Not the coldest Mars gets, the average. A place on this planet, under our sun, wrapped in our atmosphere, was regularly hitting temperatures colder than the daily average on another planet entirely. How? How does that happen? How does a place on Earth, a planet that has been bathed in solar energy for 5 billion years, a planet covered in oceans and wrapped in a greenhouse atmosphere, a planet where life thrives in almost every corner. How does one part of it get this cold? That is what this entire video is about. And I promise you, the answer is not simple. It is not just, well, it's at the South Pole, so it's cold. That is like saying Usain Bolt is fast because he runs quickly. It tells you nothing. The real answer is a layered, interconnected, breathtaking system of geography, atmospheric physics, ocean dynamics, and deep planetary history that has been building for 40 million years. Over the next hour and 20 minutes, We are going to dismantle every single piece of that system. We are going to understand not just that Antarctica is cold, but why, at the deepest possible level. And by the end of this video, I promise you will look at this continent completely differently. Antarctica is not just a cold place. It is a machine, a perfect, ancient, self-reinforcing engine of cold that has been running non-stop since before our species existed. And once you understand how it works, you will understand something profound about how our entire planet operates. All right, reason number 1, and this is the foundation that everything else is built on. So I need you to really understand this properly. Not just nod along, but actually get the physics of it. Because everything else we talk about in this video is going to stack on top of this. Antarctica is cold, first and foremost, because of where it sits on this planet. Antarctica is centered almost perfectly on the geographic South Pole, right at the bottom of the Earth, at 90 degrees south latitude. And I need you to understand what that actually means in terms of how sunlight hits that part of the planet. Because this is where the physics gets really interesting. The Earth orbits the Sun tilted on its axis at 23.5 degrees. That tilt is the reason we have seasons. It controls the angle at which sunlight strikes different parts of the planet at different times of the year. And that angle is everything, because it's not just that sunlight arrives that matters. It's how it arrives. The angle of incidence determines how concentrated the energy is. Think about it this way. Imagine you have a flashlight, a torch, and you're shining it at a flat table. If you hold that torch directly above the table, pointing straight down, you get a nice tight circle of light. Bright, concentrated, intense. All the energy from that torch is packed into a small area. Now take that same torch, same battery, same bulb, same amount of light coming out, and tilt it to a really low angle, almost sideways, grazing across the table. What happens? That same amount of light is now spread across a huge elongated oval. The total energy hasn't changed at all, but the intensity, the energy per square centimeter, has dropped dramatically. That is exactly what happens with sunlight at the South Pole. At the equator, the sun passes nearly overhead for most of the year. Sunlight comes in close to perpendicular to the surface. Energy is concentrated. That's why the tropics are hot. The sun is delivering maximum energy per square meter. At the South Pole, the sun, even when it's technically up during summer, never rises more than 23.5 degrees above the horizon. Even at its highest, it's barely scraping above the horizon. The sunlight is coming in at this incredibly shallow, grazing angle. That same solar energy is being spread over a huge area, and on top of that, it has to travel through a much thicker slice of atmosphere at that low angle, getting scattered and absorbed more before it even reaches the surface. The result is that even on a clear midsummer day at the South Pole, the solar energy arriving per square meter is only a tiny fraction of what hits the equator at the same moment. The sun is up. It's just not doing much. And for 6 months of the year, Antarctic winter, the sun is not up at all. 0. Complete darkness. We'll come back to what happens during that darkness in a moment, because it is absolutely brutal. But here's where Antarctica separates itself even further from the Arctic. Because the Arctic is also at a pole, right? The North Pole is also at 90 degrees latitude. So why is Antarctica so much colder than the Arctic? 2 words: elevation and land. The Arctic is an ocean. The Arctic Ocean. It sits at sea level, covered in sea ice that is typically only a few meters thick. Beneath that ice is liquid ocean water that carries heat from lower latitudes. The Arctic, despite being at the pole, is connected to the rest of the planet's ocean heat system. Antarctica is a continent. Solid rock. And sitting on top of that rock is an ice sheet of almost incomprehensible thickness. The Antarctic ice sheet averages 2,160 meters thick, over 2 kilometers of solid ice from surface to bedrock. In some places, it exceeds 4,800 meters, nearly 5 kilometers thick. The surface elevation of the Antarctic interior, the part where the coldest temperatures are recorded, sits at between 3,000 and 4,000 meters above sea level. Vostok Station, where that 1983 record was set, is at 3,488 meters. The highest point of the ice sheet, called Dome A or Dome Argus, sits at 4,093 meters above sea level. For comparison, the highest mountain in Africa, Kilimanjaro, peaks at 5,195 meters. Antarctica's ice surface is sitting at the elevation of a significant mountain range, covering an entire continent. And altitude matters enormously for temperature. The atmosphere gets colder as you go higher. The standard lapse rate, the rate at which temperature drops with increasing altitude, is about 5 degrees Celsius per 1,000 meters. So compared to sea level, being at 3,500 meters of altitude alone accounts for roughly 22 degrees of additional cooling. 22 degrees. Just from being high up. So Antarctica is already receiving very little solar energy because of its polar location. It compounds that by being thousands of meters above sea level, where the atmosphere is thinner and colder, and it has no warm ocean beneath it to provide any buffer. The Arctic cold, in comparison, is moderated by the ocean beneath. Vostok Station has no ocean beneath it. It has 3,700 meters of solid ice, and underneath that, bedrock that hasn't seen direct sunlight in tens of millions of years. These two factors alone, polar location and extraordinary elevation, would make Antarctica the coldest continent on Earth, even if nothing else was working against it. But we have barely scratched the surface. 6 more reasons to go. Okay, reason number 2. And this one is going to make you think about color and light in a way you probably never have before. Antarctica is white. Almost completely, uniformly, blindingly white. And that whiteness, that color, is one of the single most powerful cold amplifying forces anywhere on this planet. To understand why, we need to talk about a concept called albedo. Albedo comes from the Latin word for white, alba. In science, albedo is a measure of how reflective a surface is. It's expressed as a number between 0 and 1. An albedo of 0 means a surface absorbs all incoming light and energy. Nothing reflects back. An albedo of 1 means a surface reflects all incoming light. Nothing is absorbed. In reality, most surfaces fall somewhere in between. Now let's run through some examples so you can feel the scale here. The open ocean has an albedo of about 0.06. Dark blue-green water absorbs nearly everything. 94% of all incoming solar radiation is soaked up by the ocean. That absorbed energy warms the water. It's why tropical oceans are warm. They are excellent at capturing the sun's energy. A dense forest, green trees, dark soil, has an albedo of roughly 0.15. Still pretty absorptive. Forests warm up well. The Sahara Desert, which we picture as blindingly bright, almost impossible to look at in direct sun, has an albedo of only about 0.3. Even the Sahara is absorbing 70% of incoming solar radiation. Fresh snow, albedo of 0.8 to 0.9. It reflects 80 to 90% of all incoming solar radiation straight back into the atmosphere and back out to space. The surface absorbs almost nothing. The Antarctic ice sheet is covered in a layer of fresh and compressed snow and ice that gives it an average albedo of around 0.8. In some areas of fresh snowfall, it reaches 0.85 or higher. So think about what is happening here. Antarctica is already getting very little solar energy delivered to it because of its polar location and the low angle of the sun. Of the small amount of energy that does manage to arrive, after fighting through all that extra atmosphere at a grazing angle, Antarctica's surface then reflects roughly 80% of it straight back into space. The surface is left with almost nothing. In energy terms, it's like Antarctica is receiving a trickle, and then throwing 80% of that trickle back before it can do anything. The surface absorbs barely a fraction of what arrives. But here's what really gets me about this. This whiteness doesn't just passively fail to absorb heat. It creates an active feedback loop, a trap, that Antarctica has been caught in for tens of millions of years, and that becomes more powerful the longer it runs. Here's how the trap works. Step 1. The ice surface is cold, so it doesn't melt much. Step 2. Because it doesn't melt, new snow accumulates on top. Step 3. That new snow is bright white and highly reflective. Albedo goes up. Step 4. Because albedo is high, more sunlight is reflected, less is absorbed. Step 5. Because less is absorbed, the surface stays cold. Step 6. Because it's cold, the ice doesn't melt. Back to step 1. Scientists call this the ice-albedo feedback loop, and it is one of the most powerful self-reinforcing climate mechanisms on Earth. Once a sufficiently large ice sheet forms, this loop kicks in and keeps it there. It is incredibly hard to break out of. The Antarctic ice sheet entered this feedback loop approximately 34 million years ago. It has not escaped since. Every year, every decade, every million years, the loop runs. The whiteness preserves the cold preserves the whiteness. Now, here's where this gets even more extreme. Everything I just described about albedo and reflection, that all assumes there's sunlight hitting the surface in the first place. But what happens during Antarctic winter? What happens when the sun completely disappears for 6 months? Because the sun does completely disappear. From around late March to late September, the interior of Antarctica receives absolutely zero direct sunlight. The sun drops below the horizon, and it stays there. Not a sunrise. Not a sunset. Just an unbroken, months-long polar night. During those 6 months, the albedo effect doesn't matter. There's nothing to reflect. But another mechanism takes over that is, if anything, even more pitiless. It's called radiative cooling. Every object that is above absolute zero temperature, 0 Kelvin, negative 273 Celsius, emits energy as infrared radiation. Everything does this. Your body is doing it right now. The ground outside is doing it. It's how heat escapes from surfaces. Normally, this outgoing heat is partially trapped by the atmosphere. Water vapor, clouds, and greenhouse gases absorb some of it and re-emit some back down to the surface. This is the greenhouse effect, and it's why Earth isn't frozen solid. But Antarctica's atmosphere, especially over the interior, is extraordinarily dry and extraordinarily clear. Almost no water vapor. It's so cold the air holds almost none. Almost no clouds over the deep interior. The atmosphere is about as transparent to outgoing infrared radiation as it gets anywhere on Earth. So during the 6 months of polar night, the Antarctic surface just bleeds its heat into space. Night after night. Week after week. Month after month. No sunlight coming in to replace it. No clouds trapping it. No moisture retaining it. Just a continuous one-way flow of energy from the surface out into the void. By the end of Antarctic winter, the surface has given up so much heat that it reaches its absolute minimum temperature. Those are the conditions under which Vostok hit negative 89. Those are the conditions under which satellites measured negative 93 on the plateau. The surface has been cooling for 6 unbroken months with nothing to stop it. And then, just when you think it might warm up, summer arrives. The sun comes back, but 80% of its energy bounces off the white surface. The albedo mirror is still there, still working. The surface gains a little warmth in summer, but not nearly enough to undo 6 months of radiative loss. And the next winter comes around and the whole thing starts again. This is the rhythm of Antarctica's cold. Summer albedo, winter radiation, year after year, century after century. 40 million years of this cycle, each one reinforcing the ice that drives the next one. All right, reason 3. And this one involves the atmosphere in a way that goes way beyond just cold air sitting over a cold surface. This one is about a structure, a large-scale atmospheric phenomenon that acts as both a generator of extreme cold and a barrier preventing any warmth from getting in. It's called the polar vortex. Now I know some of you have heard this term before, usually in dramatic news headlines when an unusual cold snap hits North America or Europe. Polar vortex unleashes Arctic blast. That kind of thing. But what most people picture when they hear those headlines, a burst of cold air escaping the Arctic, is actually a description of the polar vortex failing or weakening, not of what it normally does. The real polar vortex is not a weather event. It's not something that comes and goes. It is a permanent, massive, spinning system of cold air that exists over both poles, essentially year-round. Over Antarctica, it is the most powerful, most consistent, most uninterrupted polar vortex on the planet. And it is a fundamental reason Antarctica stays as cold as it does. Let me explain how it forms and why it's so powerful over Antarctica specifically. In late autumn, as Antarctica heads into winter, sunlight disappears from the polar region. The stratosphere, the layer of atmosphere between roughly 12 and 50 kilometers above the surface, begins to cool rapidly over Antarctica as it loses its heat source. This cooling makes the stratospheric air denser and heavier. It starts to sink and spread outward from the pole. Now here is where the Earth's rotation comes in. The Earth is spinning, and that spinning deflects moving air. It deflects it to the left in the southern hemisphere. This is called the Coriolis effect, named after the French mathematician who first described it. Because of the Coriolis effect, the cold air trying to spread outward from the pole doesn't just flow straight out. It curves, organizing itself into a large-scale rotation around the pole. What you end up with is a massive column of cold air spinning around Antarctica, clockwise when viewed from above the South Pole, extending from the stratosphere all the way down toward the surface. Cold air on the inside, warmer air from lower latitudes on the outside. A pressure difference between the inside and outside of the vortex creates strong winds circling the continent, winds that act as a barrier. And here's the key point. The colder the interior gets, the stronger the pressure difference, the stronger the barrier winds, the more isolated the cold becomes. The vortex feeds on itself. Cold creates the vortex. The vortex preserves the cold, which makes the interior colder, which strengthens the vortex. Another feedback loop. Antarctica is full of these. Now, both poles have a polar vortex. So why is Antarctica so much more powerful and persistent than the Arctic's? Geography. Entirely geography. The Arctic vortex is constantly being disrupted. The land masses surrounding the Arctic, North America, Greenland, Eurasia, have enormous mountain ranges. The Rockies, the Himalayas, the Urals. These mountain ranges force the atmospheric flow into large waves, called Rossby waves, that buckle and distort the polar vortex. The Arctic vortex gets squeezed, stretched, broken apart, and displaced from the pole on a regular basis. When it weakens and breaks down, cold air escapes southward. That's those polar vortex headlines you see. And warm air rushes north to partially replace it. The Arctic vortex is dynamic, irregular, and leaky. Antarctica's vortex is the opposite. Antarctica is a round, elevated, symmetrical continent sitting right at the center of the Southern Ocean, with no major landmasses nearby to disrupt the atmospheric flow. The westerly winds circling Antarctica flow in clean, uninterrupted rings. The polar vortex over Antarctica is tight, symmetrical, powerful, and extraordinarily stable, maintaining its integrity through most of the winter without breaking down. Warm air from the north simply cannot push through it. The result is that Antarctica's interior is sealed off from the rest of the atmosphere for most of the year. Any warmth that does try to move southward gets deflected by the vortex long before it reaches the deep interior. The cold that builds up inside stays inside. But that's just the upper atmosphere. At the surface, the polar vortex helps drive something even more immediately terrifying. Katabatic winds. Katabatic. From the Greek word katabino, to go down, to descend. Katabatic winds are gravity-driven winds that form when cold, dense air on a high-elevation surface flows downhill under the pull of gravity. And on the Antarctic plateau, the conditions for katabatic winds are essentially perfect and almost permanent. The interior plateau sits at 3,000 to 4,000 meters elevation. The air over that plateau, cooled by the mechanisms we've already discussed, is extraordinarily dense and heavy, far heavier than the air over the ocean thousands of meters below. Gravity pulls it toward the coast, and crucially, Antarctica's ice surface is smooth enough and open enough that this descending air faces almost zero friction or obstruction. It just accelerates, and keeps accelerating as it falls toward the sea. The speeds these winds reach are extraordinary. Katabatic winds in Antarctica regularly sustain at 150 to 200 kilometers per hour. During peak events, gusts have been recorded exceeding 320 kilometers per hour. Let me put that in context. Hurricane-force winds, the category that devastates coastlines and flattens buildings, begin at around 120 kilometers per hour. Antarctica's katabatic winds regularly exceed that. The strongest recorded gusts match an EF4 tornado. And these aren't occasional storm events. Certain parts of the Antarctic coast, the Adélie land coast near France's Dumont-d'Urville station, experience katabatic winds so frequently and so intensely that they are called the windiest places on Earth. Average wind speeds there exceed 80 kilometers per hour, and that's the average, including calm periods. When you factor in wind chill, the additional cooling effect of wind moving across skin or any warm surface, the effective temperatures during Antarctic katabatic events frequently exceed -80 and -90 Celsius wind chill. An unprotected human in those conditions would be in serious danger within 1 to 2 minutes. Now let's talk about the ice itself in more depth. Because we've been talking about the ice as a backdrop, as the surface that reflects sunlight, as the elevated platform, as the thing that got built over millions of years. But the ice is not just scenery. The ice is an active machine. It creates cold, it stores cold, and it does something remarkable with the atmosphere directly above it that is responsible for the most extreme temperature readings ever recorded anywhere on this planet. Let's start with the basics of how the ice sheet works as a cold reservoir. The Antarctic ice sheet is the single largest mass of freshwater ice on Earth. 5 million cubic kilometers. The numbers are difficult to wrap your head around, so let me try a few comparisons. If you took all the ice in Antarctica and melted it, which, again, we do not want to do, the resulting water would raise global sea levels by approximately 58 meters. 58 meters! The Statue of Liberty is 93 meters tall, including the base. We're talking about enough water to submerge the entire coastal infrastructure of human civilization. Every port, every beach city, every river delta, underwater. It took between 34 and 40 million years to build this ice sheet. That is not an exaggeration. Antarctica began glaciating around 34 million years ago, when plate tectonics separated it from South America and Australia, cutting off the warm ocean currents that had been keeping it temperate. As it cooled, ice formed. The albedo feedback loop kicked in. The polar vortex strengthened. The ice built up layer by layer, year by year, millennia by millennia, compressing under its own weight into denser and denser crystalline forms. This ice is ancient in a way that is hard to conceptualize. The deepest ice cores drilled from the East Antarctic Plateau have brought up ice that is 800,000 years old. And trapped inside that ice, in tiny microscopic bubbles, is air from 800,000 years ago. Actual, ancient atmosphere, perfectly preserved in the ice. Scientists can extract those bubbles and measure exactly what the atmosphere was like: CO2 levels, methane concentrations, temperature proxies, going back almost 1 million years before the first modern human ever drew breath. What does that record show? It shows that Antarctica's cold is not new. It has cycled through ice ages and warmer interglacial periods, but it has never thawed. Even during the warmest interglacials, periods when the rest of the planet was significantly warmer than today, the interior of Antarctica remained frozen. The deep cold has been persistent for millions of years. The ice sheet is extraordinarily stable over geological timescales. Now, here's what the ice does physically to the temperature at the surface. And this is the piece that directly explains how those record-breaking temperatures happen. We talked about radiative cooling earlier, how the surface bleeds heat into space during the polar night. As that cooling happens, the surface of the ice sheet gets colder and colder. The air right at the surface also gets colder, and this creates something called a temperature inversion. Normally, in the atmosphere, temperature decreases as you go higher. The standard lapse rate. You climb a mountain, it gets colder. That's normal. But over Antarctica in winter, something flips. The surface of the ice cools so rapidly and so dramatically through radiative emission that the air touching the surface becomes colder than the air a few hundred meters above it. Temperature actually increases as you move away from the surface upward. This is a temperature inversion, and what it means practically is that the coldest air in the entire atmospheric column is sitting right at the ground, right at the surface where measurements are taken, where instruments are, where human beings stand. The inversion traps that cold air at the surface. In normal conditions, surface air mixes upward. Convection stirs things around. The coldest air at the surface gets mixed with slightly warmer air above. Temperatures moderate. During a temperature inversion, That mixing doesn't happen. The cold air is denser than the warmer air above, so it just sits there, pools, concentrates, gets colder still from continued radiative emission. This is the direct physical mechanism behind Vostok's -89. 2. The entire winter at Vostok is essentially one long temperature inversion event, with the surface progressively cooling through radiative emission, the cold air pooling deeper and deeper, and eventually reaching temperatures that genuinely have no parallel anywhere else on Earth's surface. And on the plateau areas, Dome A, Dome Fuji, the areas where the 2010 satellite readings of -93 were detected, the inversions are even stronger, because those areas are even more elevated, even more isolated from any warm air influence, and have even less atmospheric moisture above them to trap any outgoing heat. The ice sheet built the plateau. The plateau creates the elevation. The elevation creates the cold. The cold creates the inversion. The inversion concentrates the cold at the surface. Every step leads to the next. And it has been doing this, uninterrupted, for millions of years. All right, let's zoom out, way out, to the ocean. Because one of the most important reasons Antarctica is so cold is not just what happens on the continent or directly above it. It is what happens in the thousands of kilometers of ocean that surrounds it, and specifically, what does not happen there. Oceans are the Earth's primary heat distribution system. They take warmth from the tropics, where the sun delivers an enormous amount of energy, and they carry it toward the poles, moderating temperatures across the planet. Without ocean heat transport, even mid-latitude regions like Western Europe would be dramatically colder than they are. The Gulf Stream, which is part of the larger Atlantic meridional overturning circulation, carries warm tropical Atlantic water northward along the eastern coast of North America and then across to northwestern Europe. This is why London, which sits at roughly the same latitude as Calgary in Canada, has winters that average above zero rather than the brutal -15 to -20 that Calgary experiences. The ocean is delivering warmth to Europe that its latitude alone would never provide. Now, what warm ocean current is delivering heat to Antarctica? None. Zero. Antarctica has no Gulf Stream equivalent, and this is not a coincidence. It is the result of a specific feature of the Southern Ocean that makes it unlike any other ocean on Earth. The Southern Ocean, the body of water surrounding Antarctica, is home to the Antarctic Circumpolar Current, the ACC. It is the largest ocean current on Earth. It carries more water than any other current, about 130 to 150 times the combined flow of all the rivers on Earth. It flows continuously, uninterrupted, in a clockwise direction around Antarctica when viewed from the South Pole. Why does it flow without interruption? Because there is no land in its way. Between approximately 55 and 65 degrees south latitude, in the belt of ocean surrounding Antarctica, there is no continent, no major island chain, nothing to block the current's path. It just flows, and flows, and flows. It has been flowing continuously for somewhere between 30 and 34 million years. Ever since the Drake Passage opened up when South America finally fully separated from the Antarctic Peninsula. Now here's what the ACC does to Antarctica's temperature situation. It creates a thermal barrier. The current itself, and the atmospheric westerly winds that drive it, form a boundary between the warmer subtropical waters to the north and the cold polar waters to the south. Warm water from lower latitudes cannot easily cross this boundary and reach the Antarctic coastline. The current diverts and deflects anything trying to push southward. The waters inside the ACC, between the current and the continent, are some of the coldest ocean surface waters on Earth, sitting near or below 0 degrees Celsius. So while continents like Europe or North America benefit from warm ocean currents moderating their climates, Antarctica is surrounded by a wall of cold water and a current that actively prevents any warm water from approaching. No maritime warmth, no oceanic moderation. The continent sits in its own thermally isolated bubble, insulated from the rest of the planet's heat budget by a relentless circular current that has been running for 30 million years. Compare this once more to the Arctic. The Arctic Ocean is connected, through the Bering Strait and various passages between the Canadian Arctic Islands and Greenland, to both the Pacific and Atlantic Oceans. Warm water does push into the Arctic. It's not a lot, but it's significant. The Arctic has a moderating oceanic influence. Antarctica does not. This oceanic isolation stacks on top of the atmospheric isolation from the polar vortex. Warm air can't get through from above. Warm water can't get through from the sides. Antarctica is sealed. Now let me tell you one more thing about Antarctica that is genuinely one of the most surprising facts about the continent. Something that completely contradicts what most people picture. Antarctica is a desert, not metaphorically, not exaggeratedly. Technically, scientifically, by the precise definition used by climatologists, the interior of Antarctica is a polar desert. A desert is defined not by heat, but by precipitation. A desert is any region that receives less than 250 millimeters of precipitation per year. Antarctica's interior receives less than 50 millimeters per year. In some parts of the East Antarctic Plateau, annual precipitation is under 20 millimeters. For reference, the Central Sahara averages around 25 millimeters. The driest parts of Antarctica are as dry as the driest desert on Earth, and it almost never snows in the traditional sense over the interior. No snowstorms, no blizzards bringing fresh snowfall. What precipitation does occur comes as diamond dust, tiny ice crystals precipitating from a completely clear sky under extremely cold, dry conditions. You can be standing in Antarctica with perfect blue sky overhead and feel these tiny crystals drifting down, glittering in the low light. Beautiful, and also a sign that the air is so cold and so dry that it cannot even form proper clouds. This desert dryness, as we touched on earlier, keeps the atmosphere extraordinarily transparent to outgoing infrared heat. Water vapor is a significant greenhouse gas. In a humid environment, water vapor captures outgoing heat and recirculates some of it back to the surface. In Antarctica's dry interior, that greenhouse blanket is almost entirely absent. Heat goes out. Nothing comes back. The cold deepens. Okay, let's step away from the science for a moment. Because I think at this point in the video, you have all the facts. You know why it's cold. You know the mechanisms. But I want you to feel it. I want you to actually imagine being in Antarctica. Because I think the human experience of this place communicates something that graphs and numbers cannot. Imagine you are a scientist at a research station on the East Antarctic Plateau. It is mid-July, deep winter. The temperature outside is -62 Celsius. Wind is blowing at about 30 kilometers per hour, which puts wind chill around -80. Getting dressed to go outside takes 20 minutes. Not because you're slow, because there are that many layers. Thermal base layer, mid-weight insulating layer, heavyweight fleece, outer windproof shell. 2 pairs of socks. Boots that weigh over 1 kilogram each and are rated to -100. Inner gloves, outer mitts. Balaclava over your entire face, except a small eye slit. Goggles. A hood over everything. You look like an astronaut on a budget. Every single piece of this system matters. It is not an exaggeration to say that the clothing you're wearing is the only barrier between you and conditions that would kill you in under 10 minutes. You step outside. The first thing that hits you, before cold, before wind, is silence. A silence so complete it has a physical quality. In the absence of any biological activity, no insects, no animals, no wind and trees, no flowing water, the world becomes acoustically empty in a way no temperate or tropical person has ever experienced. You can hear your own heartbeat. You can hear the creak of your clothing. Then the cold arrives. Your first breath feels like inhaling powdered glass. It's not painful exactly. It's more like a total reset of what breathing is supposed to feel like. The inside of your nose crystallizes with the first inhale. Your eyelashes begin frosting within seconds. Any skin left exposed, if you made the mistake of leaving a strip of forehead uncovered between balaclava and goggles, begins burning immediately and will be numb within a minute. The horizon is visible for hundreds of kilometers in every direction. The air is so dry and clear that there is essentially zero atmospheric haze. The sky overhead is a deep, almost unreal blue-black, close to what you see in photographs from high-altitude aircraft. The sun is below the horizon, has been for 3 months, and the stars are extraordinary. Not twinkling the way they do through humid lower-altitude air, just burning, fixed, impossibly bright. You understand why people call the sound of crystallizing breath the whisper of stars. The scale of the place is hard to process. You are standing on top of over 2 kilometers of solid ice, in every direction, white, flat, unending. You are more isolated from other human beings than almost any other place you could stand on Earth. The nearest humans who are not in your small station might be hundreds of kilometers away at another research camp. The nearest city is thousands of kilometers away, across one of the stormiest oceans on the planet. People who winter over in Antarctica, who choose to stay through the full 6 months of polar night, describe the experience as the most psychologically extreme thing they have ever done. The continuous darkness destroys your body clock within weeks. Circadian rhythm, the internal biological cycle that governs sleep, metabolism, hormone production, depends on light. Take away light for 6 months, and the system breaks down. Some people sleep 12, 14 hours a day. Some cannot sleep more than 4. Time becomes meaningless. The sensation of day and night evaporates. The isolation compounds this. During the winter, no aircraft can reach the deep interior stations. The cold is too extreme for aircraft engines and hydraulic systems to function reliably. You cannot leave if you want to. You cannot receive visitors. The outside world, the rest of civilization, exists only through satellite internet, which is limited and intermittent. And yet, almost everyone who has done it says they would go back. There is something about Antarctica that changes people in a way that is very hard to explain without having been there. The silence, the clarity, the sense of being in a place that is genuinely, authentically, completely untouched by civilization. There are no roads, no buildings beyond a handful of research stations, no pollution, no noise. You are in a place that exists on its own terms, completely indifferent to human activity, operating according to physical laws that predate our species by tens of millions of years. Researchers who have spent time in Antarctica frequently describe it as the closest thing on Earth to being on another planet. And given the temperatures, the dryness, the isolation, the alien landscape, that comparison is not as hyperbolic as it sounds. I need to take a turn in this video now, because everything I have described in the last hour, the ice, the albedo, the vortex, the circumpolar current, I have been describing as permanent, as a fixed feature of the planet, the ancient cold that has been running for 40 million years. But things are changing, and the changes are happening fast enough, and are serious enough, that I would be doing you a disservice if I spent 90 minutes on Antarctica without talking about it. Antarctica is warming, not uniformly. The deep interior of the East Antarctic Plateau, the coldest part, has shown relatively modest warming so far, and in terms of absolute temperature, it remains overwhelmingly, brutally cold. But the edges of the continent, and particularly the Antarctic Peninsula, the arm of land that extends northward from the main continent toward South America, have experienced some of the fastest regional warming rates recorded anywhere on the planet in recent decades. The Antarctic Peninsula has warmed by nearly 3 degrees Celsius since the 1950s. That is roughly 3 times the global average rate of warming over the same period. And in the context of ice that has existed for thousands and tens of thousands of years, 3 degrees is not a small number. The most visible consequences have been in the ice shelves. Ice shelves are the parts of the Antarctic ice sheet that have flowed out from the continent and are now floating on the ocean. They are attached to the glaciers on land behind them, and they act as buttresses, physical barriers that slow the seaward flow of those glaciers. Think of them like a cork in a bottle. As long as the cork is there, the contents stay put. In 1995, the Larsen A ice shelf, 1,500 square kilometers of floating ice, disintegrated over the course of a few weeks. Gone. In 2002, something even more shocking happened. The Larsen B ice shelf was approximately 3,250 square kilometers, about the size of Rhode Island, or slightly larger than Luxembourg. It had existed continuously for at least 10,000 years, through the entire Holocene, through the whole of recorded human history, since before the pyramids were built. Scientists knew it was thinning and weakening. They expected it to break up eventually, over years, maybe decades. Instead, beginning in late January 2002 and continuing through early March, Larsen B disintegrated. The entire shelf shattered into thousands of icebergs and spread across the Weddell Sea. The collapse was essentially complete within 35 days. 35 days. An ice shelf that had survived 10 millennia was gone in 5 weeks. Scientists watching the satellite data in real time described their reaction as one of genuine disbelief. The models had not predicted this speed. The expectation had been a gradual process. What they were watching was catastrophic, near instantaneous collapse, and the consequences were immediate. The glaciers that Larsen B had been buttressing, holding back, began accelerating toward the ocean almost immediately. Within months, they were flowing 3 to 8 times faster than before. Without the cork, the bottle was draining. This is the fundamental danger of ice shelf collapse. It is not the collapse itself that directly raises sea levels much. Floating ice, like ice in a glass of water, doesn't raise the level when it melts. What matters is what the collapse unleashes. The glaciers behind the shelves, the land ice. That is where the sea level rise comes from. And this brings us to the glacier that is keeping climate scientists awake at night more than any other on Earth. Its name is Thwaites Glacier. Some researchers have started calling it the Doomsday Glacier. That name sounds sensationalist. The science behind it is not. Thwaites Glacier is located in West Antarctica. It is enormous, roughly the size of the state of Florida, or about the size of Great Britain. Right now, it is contributing around 4% of global sea level rise per year, and that contribution is increasing. If Thwaites were to disintegrate completely, it would add approximately 65 centimeters, about 2 feet, to global sea levels by itself. But the real worry about Thwaites is not what it would do alone. It is what it would trigger. Thwaites acts as a keystone for a large portion of the West Antarctic ice sheet. If Thwaites destabilizes sufficiently, it could set off a cascade, a chain reaction of glacier acceleration and ice shelf collapse across West Antarctica. The total sea level contribution of a full West Antarctic ice sheet collapse is estimated at around 3 meters. Over 3 meters of additional sea level globally. Every coastal city on Earth would be transformed. The timeline for this is not tomorrow. It is not next year. Even under the worst-case scenarios, full collapse of West Antarctica would take centuries. But the beginning of that process, the triggering, may already be underway. And once certain feedback thresholds are crossed, the process becomes self-sustaining regardless of what happens to emissions afterward. One study published in 2023 found that the ocean water beneath Thwaites' ice shelf has warmed by more than 1 degree Celsius since measurements began. Warm water is getting under the glacier and melting it from below. The glacier's grounding line, the point where it lifts off the bedrock and begins floating, has been retreating inland at an accelerating rate. This is the warning that Antarctica carries for the rest of the world. The mechanisms that make it cold, the albedo loop, the polar vortex, the ocean circulation, are powerful. But they are not unconditional. They can be pushed. They can be weakened. And at the margins, where ice meets warming ocean, the pushing has already begun. Okay, we have covered everything. An hour and 20 minutes of science, history, physics, and human experience. And now it is time to bring it all home. To answer the original question, as cleanly, as completely, and as powerfully as possible. Why is Antarctica the coldest place on Earth? Because of 7 mechanisms, each one significant on its own. Together, absolutely overwhelming, creating a system of cold so complete and so self-reinforcing that no other place on Earth comes anywhere close. Let me run through all 7 one final time. Reason 1. Polar location. Antarctica sits almost perfectly on the South Pole, at 90 degrees latitude. The sun's rays arrive at an extreme grazing angle, spread across an enormous area, delivering a tiny fraction of the energy per square meter compared to anywhere closer to the equator. 6 months of complete polar darkness every year means 0 solar input for half of every annual cycle. This is the foundation. Everything else builds on this. Reason 2. Extraordinary elevation. The Antarctic ice sheet has built a continent-spanning elevated plateau sitting at 2,000 to 4,000 meters above sea level. Temperature drops roughly 6.5 degrees per 1,000 meters of altitude. Being at 3,500 meters alone accounts for over 20 additional degrees of cooling compared to sea level. The Arctic, for comparison, sits at sea level. Antarctica sits on a frozen mountain range covering an entire continent. Reason 3. The albedo mirror. Antarctica's ice and snow surface reflects 80 to 85% of all incoming solar radiation straight back into space. Even the little heat that manages to arrive gets bounced away before the surface can absorb it. The ice albedo feedback loop locks this system in permanently. The ice preserves cold, the cold preserves ice, the ice preserves cold, a trap that has been running for 40 million years. Reason 4. Radiative cooling and dry air. During 6 months of polar night, the surface radiates its heat into space through an atmosphere with almost no water vapor or clouds to block it. Temperature inversions form. The coldest air pools and concentrates right at the surface rather than mixing upward. This is the direct mechanism behind the record temperature readings at Vostok and on the East Antarctic Plateau. The planet's driest atmosphere, less than 50 millimeters of precipitation per year, is also the planet's most transparent to outgoing heat. Reason 5. The polar vortex and katabatic winds. A permanent spinning wall of cold air surrounding Antarctica blocks the exchange of heat with warmer latitudes. The most stable, most powerful polar vortex on Earth, undisturbed by any surrounding mountain ranges, seals the cold in and keeps warm air out through most of the year. And at the surface, katabatic winds, gravity-driven winds descending from the plateau, regularly exceed 200 to 300 kilometers per hour, stripping heat from every surface they contact. Reason 6. The Antarctic circumpolar current. The largest ocean current on Earth rings Antarctica with a wall of cold water, preventing warm subtropical ocean currents from reaching the continent. While ocean heat transport moderates temperatures in Europe, North America, and coastal Asia, Antarctica receives none of this benefit. Its ocean surroundings amplify its isolation rather than moderating it. The ACC has been running for 30 million years and has been keeping Antarctic waters cold for every one of them. Reason 7. The ice sheet itself. 2 miles of ancient compressed ice storing cold the way a battery stores charge, providing the elevation that drives further cooling, creating the temperature inversions that concentrate cold at the surface, preserving 800,000 years of climate history in its layers, insulating the bedrock from any warmth, and powering the albedo feedback that started this whole list. 7 reasons. Every single one enormous. Every one interdependent with the others. Remove any one of them, and Antarctica is still brutally cold. Put them all together, and you get something that has no equal on Earth. Temperatures colder than Mars. Winds faster than EF4 tornadoes. 6 months of darkness followed by 6 months of a sun too weak and too white reflected to warm anything meaningful. No other place has all 7. The Arctic has reason 1, polar location, but lacks elevated land ice, lacks the stable polar vortex, lacks the circumpolar current, and has warm ocean beneath it. It gets cold. It does not get Antarctic cold. Siberia gets phenomenally cold in winter, -60, -67, but it thaws every summer. The cold is seasonal, and it is nowhere near Antarctica's interior even in winter. The Tibetan Plateau has elevation, but it is not at the pole. It receives monsoon moisture. It has warm air pushing onto it from the south. Only Antarctica has all 7. Only Antarctica has built, over 40 million years, a system so comprehensive that it produces temperatures colder than another planet. And I want to leave you with one final thought. Antarctica is often discussed in the context of what it is losing: ice shelves collapsing, glaciers accelerating, warming at the margins. And that is real, and it matters enormously. But in the midst of all the justified concern about what is changing at the edges, it is worth pausing to appreciate what Antarctica still is. It is the last great wilderness on Earth, a continent larger than Europe with almost no permanent human presence, a place where the ice has been building and breathing for 40 million years, storing the history of our planet's atmosphere in its layers. A place so remote and so cold and so extreme that it has resisted not just human settlement, but human understanding for most of our history. The first humans to reach the South Pole, Amundsen's team in December 1911, arrived barely over 100 years ago. The first confirmed sighting of the continent was in 1820. In the entirety of human civilization, stretching back 10,000 years to the first cities, we were completely unaware this place existed for 99% of that time. And even now, after a century of research and exploration, we are still learning fundamental things about how it works, how it affects the rest of the planet, and what it will do as the world warms around it. Antarctica is not just the coldest place on Earth, it is one of the most important. It holds the history of our climate. It drives the circulation of the world's oceans. It reflects enough solar energy to measurably influence global temperature balance. It stores enough ice to rearrange every coastline on Earth. Understanding Antarctica is not just about understanding one extreme place. It is about understanding the planet we all live on. The cold at the bottom of the Earth is not separate from the warmth everywhere else. It is part of the same system, the same machine, the same Earth, the frozen throne, the coldest place that exists, the oldest cold that runs, the last wilderness standing, and the place that, more than any other on this planet, deserves our attention right now. If you made it to the end of this video, genuinely, thank you. This was a long one. Drop a comment below. Tell me which part hit you the hardest. Was it the temperature records? The albedo feedback loop? The weights? The experience of actually being there? If you learned something today, smash that like button. It genuinely helps the channel. Subscribe if you want more deep dives like this one. We go long on this channel and we go deep. Antarctica has a lake under it, not a small puddle, a massive liquid lake. It's called Lake Vostok, and it sits beneath nearly 4 kilometers of solid ice. It is roughly the size of Lake Ontario. It has been completely sealed off from the rest of the world. No contact with the surface atmosphere, no sunlight, no connection to any other body of water. For somewhere between 15 and 25 million years. Scientists drilled down to it in 2012, and when they finally broke through into the water, they were accessing a body of liquid that had been isolated from the rest of life on Earth since before our earliest hominid ancestors existed. The water in that lake has not touched air since before humans evolved. Let that sit with you for a second. And here's why that matters beyond just being a cool fact. If liquid water can exist under 4 kilometers of Antarctic ice, sealed off from sunlight and warmth for millions of years, what does that tell us about the possibility of life under the ice sheets of Jupiter's moon Europa or Saturn's moon Enceladus? It tells us that liquid water under ice in total darkness is not just possible. We have a working example of it right here on Earth. Antarctica is not just a climate laboratory. It is a test bed for astrobiology, for the search for life beyond Earth. Fact number 2. Antarctica is the only continent on Earth with no native human population. Every other continent, every single one, has human populations that have lived there for thousands of years. People adapted to the Sahara, to the Arctic tundra, to the Amazon, to the Australian outback. No human population has ever permanently settled Antarctica. In the entire history of our species, hundreds of thousands of years of humans spreading across this planet, no one ever made it their home. The first person to even see Antarctica was in 1820. The first to reach the South Pole was Roald Amundsen in 1911. For 99% of human civilization, this entire continent was completely unknown to us. Fact number 3. Despite being a desert that receives almost no precipitation, Antarctica holds 70% of Earth's entire freshwater supply locked in its ice. 70%. All the rivers, all the lakes, all the groundwater, all the glaciers outside Antarctica, combined, they make up the remaining 30% of Earth's fresh water. Antarctica alone holds more than double all of it. If you wanted to solve the global freshwater crisis purely by volume, the answer is sitting at the bottom of the Earth. Obviously, we can't access it, and obviously melting it would be catastrophic. But the sheer scale of what is stored there is extraordinary. Fact number 4. Antarctica has active volcanoes. I know. You'd think the coldest place on Earth and volcanoes would be mutually exclusive. But Mount Erebus, sitting on Ross Island just off the Antarctic coast, is one of the few volcanoes on Earth with a persistent lava lake, a lake of molten rock that has been continuously active for decades. The contrast is almost surreal. You have outside air temperatures of -40, -50 Celsius, howling polar wind, blinding white ice in every direction, and in the middle of it, a crater filled with churning lava. Antarctica contains multitudes. And the final fact. The ice in Antarctica is so heavy, such an incomprehensible mass pressing down on the continent beneath, that it has actually pushed the bedrock of Antarctica below sea level in many areas. The weight of the ice has literally depressed the continent into the Earth's mantle. If you removed all the ice tomorrow, Antarctica would slowly, over thousands of years, rebound upward as the weight was lifted, in a process called isostatic rebound. Parts of it would eventually rise by hundreds of meters. The continent would reshape itself. Antarctica, as we know it, is not even its true shape. It is a compressed version, squashed down under the weight of its own ancient ice. That is Antarctica, a place with a subglacial lake older than humanity, the only continent no human ever called home, the keeper of 70% of Earth's fresh water, a continent with active volcanoes buried in ice, and a landmass so heavy with ice that it has sunk into the planet beneath it.